This video will provide you an overview of how the outer, middle, and inner ear contribute to the senses of hearing, balance, and spatial orientation. Let's begin with the outer ear. The auricle, what we usually refer to as our ear, has a number of distinguishable features. The helix, the crus of the helix, the antihelix, the crura of the antihelix, the triangular fossa, the scaphoid fossa, the antitragus, the cavum concha, the lobule, and the external auditory meatus.
The external auditory meatus is made up of both the cartilaginous and a bony portion. The cartilaginous portion is lined with sebaceous glands, which produce cerumen, or earwax, to help protect and clean the ear. The external auditory meatus is located in the tympanic part of the temporal bone. On to the tympanic membrane, also known as the eardrum. The majority of the tympanic membrane is comprised of 3 layers. The lateral layer is epithelial, the central layer is fibrous, and the medial layer is mucosal. The tympanic membrane is concave in shape, and its centermost point is called the umbo.
A potential pathology of the outer ear is external auditory atresia, which is a rare congenital disorder in which the external auditory meatus is never fully formed and causes a conductive hearing loss. Moving on to the middle ear, also known as the tympanic cavity. There are 3 portions of the middle ear: the epitympanum, the mesotympanum, and the eustachian tube. The epitympanum is above the tympanic membrane and serves as a space for the ossicles. The mesotympanum is the space starting at the top of the tympanic membrane. And the eustachian tube, shown here, serves to maintain balanced air pressure in the middle ear by letting air enter or escape.
Next, we'll discuss the ossicles of the middle ear, which are a series of bones that help convey the sound to the inner ear. The tympanic membrane is connected to the manubrium of the malleus. The head of the malleus is attached to the body of the incus via their articular surfaces. The lenticular process of the incus attaches to the head of the stapes, forming the incutostapedial joint. Finally, the footplate of the stapes sits on the oval window. The middle ear has 6 walls, which we commonly visualize as a cube. Each wall has important features. The lateral wall is formed by the tympanic membrane and the squamous portion of the temporal bone. On the medial wall reside the oval window and round window, the promontory of the cochlea, and the prominence of the horizontal semicircular canal.
On the posterior wall reside the pyramidal eminence, the chorotympany nerve, and the fossa incutus. And on the anterior wall reside the canal of the tensor tympani muscle, the cochleariform process, and the entrance of the eustachian tube. The other 2 walls are of less importance to the process of hearing.
The ossicles are held in place by a variety of ligaments. Additionally, there are muscles that contract to protect the auditory system in case of a damagingly loud sound. One pathology of the middle ear is otitis media, which is an infection of the middle ear that causes inflammation and possible buildup of fluid. This is due to the inflammation of the eustachian tube, which prevents fluid that would usually drain from the ear from escaping.
Moving on to the inner ear, the oval window leads to the vestibule of the inner ear, which serves as the entrance to the cochlea. The cochlea is comprised of liquid-filled tubes that run through the petrous portion of the temporal bone. 2 of these tubes, the scala vestibuli and the scala tympani, are separated by a 3rd membranous tube, the scala media. While the scala vestibuli and scala tympani are regarded as 2 separate tubes, they actually communicate at the apex of the cochlea at a point known as the helicotrema.
Both the scala vestibuli and scala tympani are filled with perilymph, a sodium-rich fluid similar to spinal fluid, while the scala media is filled with endolymph, a potassium-rich fluid. The membrane between the scala tympani and the scala media is known as the basilar membrane. The membrane separating the scala media and scala vestibuli is known as Reisner's membrane.
On the basilar membrane resides the organ of Corti, which is the end organ for hearing. When the oval window is stimulated by the stapes, the perilymph in the scala vestibuli shifts, which in turn causes the perilymph in the scala tympani to shift due to the communication at the helicotrema. To allow for this displacement of fluid, the round window bulges outward.
The movement of the perilymph causes both Reisner's membrane and the basilar membrane to shift, but the movement of the basilar membrane is more pronounced and more important for the function of the organ of Corti. As the basilar membrane moves, the cilia of the outer hair cells shear against the tectorial membrane, which causes a firing of the neurons embedded in the hair cells.
When this firing occurs, it sends a signal through the nerve fibers, which subsequently form the spiral ganglion.
There are also inner hair cells, whose cilia are not embedded in the tectorial membrane. The inner cilia are significantly more difficult to cause to shear because they rely on the turbulent flow of endolymph, which occurs only when the basilar membrane is most disturbed.
The basis of tonotopic organization of the cochlea is due to the structure of the basilar membrane. At the base, the basilar membrane is thicker and narrower, but as it reaches the apex, the basilar membrane becomes thinner and wider. Due to this, the basal portion of the basilar membrane is more stimulated by high-frequency sounds, while the apex is more stimulated by low-frequency sounds.
The spiral ganglion resides in the medullus, which forms the central core of the cochlea. Then, it travels as the cochlear nerve through the internal auditory canal.
To give you a sense of scale, here is an image of an actual organ of Corti. Notice that in order to get a clear look at the organ of Corti, it is necessary to magnify to a point that individual cells are visible.
Let's move on to the vestibular system. In addition to serving as the entrance for the cochlea, the vestibule also houses the utricle and saccule. These two structures, in addition to the semicircular canals, form the vestibular system. The utricles and saccule sense organs are called maculae. Like the organ of Corti, they feature hair cells. However, their cilia are embedded in a gelatinous layer with calcium carbonate deposits, known as otoconia, on top. The inertia of the otoconia is greater than that of the gelatinous membrane, which causes it to shift and the cilia embedded within it subsequently shear and fire their neurons. The macula of the utricle detects horizontal acceleration, while the macula of the saccule detects vertical acceleration.
On to the semicircular canals. There are 3 semicircular canals, and they are angled at roughly 90 degrees from each other. They are called the superior, posterior, and horizontal semicircular canals. The superior and posterior canals share a crus, called the common crus. Each canal detects a different type of angular acceleration. The superior canal detects pitch, the posterior canal detects roll, and the horizontal canal detects yaw. Semicircular canals connect to the utricle via the ampullae, which is where their sense organs reside, called cristae. Cristae are very similar to maculae in that the cilia are embedded in a gelatinous layer, here called the cupula. The shearing of these cilia is dependent on the movement of the cupula, which is moved by the shifting of the endolymph within the ampullae and semicircular canals.
One last pathology, that of the inner ear, Meniere's disease. It is caused by an overproduction of endolymph, which results in a bulging and rupturing of the scala media, semicircular canals, utricle, and saccule. This rupturing can cause an ongoing sensation of vertigo and progressive hearing loss. In conclusion, the auditory and vestibular systems are comprised of an elaborate chain of structures that allow us to hear the world around us and maintain our spatial equilibrium.